Okay, so welcome back to this next video in which we are discussing atherosclerosis. Okay, right. So we're in the process of discussing the structure of low-density lipoprotein particles. Okay, right. So the key lipid molecule that low-density lipoproteins, or LDL particles, actually transport around the blood is cholesterol, as well as cholesterol esters, which are esters of cholesterol molecules. Okay, so we now need to discuss the structure of cholesterol and also the structure of these cholesterol esters, and where the free cholesterol molecules and also the cholesterol esters are stored within this LDL molecule. Then we will have completed our structure of LDL and we'll be able to move on to the pathogenesis of atherosclerosis. Okay, right. So let's start off then with the structure of free cholesterol. Okay, now, cholesterol is a sterol, and sterols are basically steroid molecules with an alcohol group fitted onto them. Okay, so let's start off with a discussion of the structure that you have within steroids. Now, this surprises people when they hear it for the first time, because people expect steroid molecules, from what they've heard within pop culture, to be molecules which are defined on the basis of their biological activity rather than on their chemical structure, when in fact steroid molecules are actually defined on the basis of their chemical structure. So let me show you the structure that you have to have within you, or something close to this, to be considered a steroid. Okay, now when we're discussing the structure of steroids and sterols, we always, absolutely always, show them in skeletal format, because if you show them in molecular format they look truly scary, and if you show them in their skeletal format they look ridiculously simple. Okay, so remember, in skeletal formulae we don't show carbon atoms. They're implicitly shown by corners and the meeting points of bonds, and we also don't show hydrogen atoms which come off carbon atoms. When you have missing bonds coming off carbon atoms, it's assumed implicitly that people understand that those are hydrogen atoms. Okay, so let's now draw the structure then of a cholesterol molecule. Okay, so you have 4 rings of carbon within a steroid structure. Okay, so this first ring here is called ring A. Then we have another 6-membered ring joined onto this, known as ring B. Then another 6-membered ring joined onto ring B, called ring C, and then finally a 5-membered ring here joined onto ring C, known as ring D. Okay, so that's the general steroid structure that you have within all steroids. And as I say, it looks ridiculously simple, and the reason it's so simple is because this pure steroid structure consists of literally nothing else than carbon atoms which are bound to each other and then to hydrogen atoms. So for instance, you've got carbon atoms bound like so, okay, all over to form this ring, and then wherever you've got missing bonds, so for instance if we look at this carbon here, you've got 2 missing bonds of that carbon. Those 2 missing bonds will be to hydrogen atoms. Okay, so really we are just seeing the skeleton of the molecule rather than the full molecule itself, which is why this sort of a formula is known as the skeletal formula. Okay, right. The other little thing I'd like to discuss before moving on to the actual structure of cholesterol is the way that we number up the carbons within a steroid structure. This will just help us when we're actually sort of looking at the structure of cholesterol. So basically the way that the carbons within a steroid structure are named is as follows. You start with this carbon up here within the A ring, and you call that number 1. You then work round rotationally. This one is number 2, this one's number 3, this one's number 4, this one is number 5, this one is number 6, this one here is number 7, this one's number 8, this one here is number 9, this one here is number 10. Okay, and now we've got to a closed ring, so we jump back over to here. This one's number 11, this one's number 12, this one's number 13, this one's number 14, this is number 15, and this is number 16, and then finally that's number 17. Okay, so we just try and do it as best as we can. Of course, we do eventually get a closed loop, and then we have to jump a little bit, but, you know, this is the best solution, basically. Okay? Right, so what you then do to convert a steroid into a sterol is that you go to carbon-free down here, okay? And at present, this carbon-free has 2 hydrogens coming off it, okay? You will take off one of those hydrogens and replace it with an alcohol group coming off. Okay, and that creates you a sterol. So any structure that then has this within it is known as a sterol. Okay, and cholesterol will indeed have this sterol structure within it. So let's now show specifically the structure of cholesterol. Okay, so firstly let's copy out our structure of the generic sterol out again. So here is ring A with an alcohol group coming off it. Here is ring B. Here is ring C, like so, and here is ring D, the 5-membered ring over here. Okay, then to turn this into cholesterol, what we do is we stick a methyl group of carbon 10 here. We also stick a methyl group of carbon 13 up there. We put a double bond between carbon 5 and carbon 6 here, and you now see why the naming system helps out. And off carbon 17 up here, we're going to attach a side chain that looks like this, and this is where I wish I'd left more space. Okay, so it's quite a beautiful side chain. It looks very symmetrical, like so. So basically, you have a 7-membered main chain here. So this is 1, 2, 3, 4, 5, 6, 7 members here. And we've attached carbon 17 to the 2nd member down here. And then off the 6th member over here, you also have a methyl group coming off, which produces this kind of nicely symmetrical group that you've got stuck off. And that then is the structure of cholesterol. Okay, so this is free cholesterol. Now, this steroid structure that you've got sitting here, these 4 rings that are all attached to each other, this is extremely hydrophobic. We've got bonds between carbon atoms and other carbon atoms, and carbon atoms and hydrogen atoms, and I've told you that neither of those bonds are very polar at all. Okay, so you are going to have this vastly hydrophobic structure here, which isn't going to interact with water at all well. And then bang, over here, we have the alcohol group, which is extremely polar and interacts with water beautifully. So you have a beautiful little polar group down here, and then this huge clunky hydrophobic bit here. Now, just before we discuss the significance of that one polar group there, okay, let me just revise our naming system now and extend it to the cholesterol structure. So let's just revise the naming of all of the members of the general steroid structure, because they're maintained when we name the members of cholesterol. So we keep this as carbon 1, we keep this as carbon 2, this stays as carbon 3, this stays as carbon 4, this stays as carbon 5, 6, 7, 8, 9, 10. So we keep the same naming system as before. It would make life extremely difficult if we changed it steroid by steroid. So we keep this core structure. Now, how do we name the new additional carbons? So we go to this one first here. We call that number 18. We then jump to this one's called 19. And then we go to these side groups, and this is I'm not going to be able to draw it on that, it's too small. So I'll copy it out over here. Okay, so here is this side chain that we have coming off carbon 17. This one is then named up as carbon 20. This one then is 21. This one is 22. This one is 23. This one is 24. This one is 25. This one is 26. And this one is 27, like so. Okay, so that's the naming of the additional carbons that are in the cholesterol structure that were not in the original sterol or steroid structure. Okay, right, so now let's, as promised, discuss the significance of having this one little glimpse of polarity in an enormous great hydrophobic structure. Okay, well the significance for this is that cholesterol molecules that are being transported in the LDL molecule can actually be transported in the phospholipid monolayer. So, for instance, I've got a nice gap here. I'm going to stick a cholesterol molecule in there, and I'll colour it in red. So that structure that I've just stuck into, that hole that I had within the phospholipid monolayer, that's supposed to be a cholesterol molecule. Now, what will happen is it will orient its one glimpse of polarity, which is this one little alcohol group here. It will orient itself within this phospholipid monolayer so that that one alcohol group is sticking out towards the outer aspect and is therefore facing the water molecules that surround our LDL molecule. And then it will have the rest of its structure, which is this huge bulky hydrophobic group here. It'll have that facing into the hydrophobic core of the LDL molecule with all of the other long chain hydrophobic tails of our phospholipids. Okay, right. Now it's finally time to discuss what's actually within the hydrophobic core of the LDL molecules. And let me just, firstly, before we do that, let me just add on a few more cholesterol molecules into the phospholipid monolayer. So you have 3 cholesterol molecules within the phospholipid monolayer of the LDL particle. Now, in the hydrophobic core of the LDL particle, you are going to have basically a storage of cholesterol esters. Now these are truly hydrophobic molecules. They do not have a single glimpse of polarity within their structures. So let's now discuss how we can turn a cholesterol molecule into a cholesterol ester. Okay, so let me show this on this other side. So let's now, on this fresh piece of paper, firstly start by redrawing out our cholesterol molecule. Okay, right, so here is this A ring of the steroid structure. Then we have our B ring of the steroid structure here. Then we have our C ring up here. And then right over here we have our D ring. Okay, and again, I haven't really left enough space for that side chain, but never mind. We then have the alcohol group coming off carbon-3 here. We have this double bond between carbon-5 here and carbon-6 here. We have this methyl group coming off carbon-10. Then, what was this carbon here called? Let's work it out. This was 10, this was 11, 12. We have a methyl group coming off carbon-13, and then coming off carbon-17 up here, we have this 7-membered side chain here. Okay, like so. So that was our cholesterol structure. Well, when I tell you that we're going to make a cholesterol ester, okay, whoops, what am I doing here? That shouldn't be like that. Cholesterol, I got a little ahead of myself and was putting the S at the start. Okay, so we're going to make an ester out of cholesterol, which will be called a cholesterol ester. Okay, there's only one real thing that we can possibly use on this entire molecule to create an ester link, and that's this alcohol group that comes off carbon-3. Okay, so what we're going to do is we're going to bring in some long-chain carboxylic acid, so some fatty acid, for instance, stearic acid for an example. Okay, and we're going to just esterify this long-chain carboxylic acid onto that alcohol group of the cholesterol molecule. So we're going to take the alcohol group off the carboxylic acid group, we'll take the hydrogen off the alcohol group, we'll bind the carbon of the long-chain carboxylic acid to the oxygen of the alcohol group of the cholesterol molecule, and we'll then have a cholesterol molecule that now has a huge, great long-chain carboxylic acid sticking out. Now, this alcohol group was the one glimpse, the one chance that the cholesterol molecule had of being polar. And now it's involved in an ester link. It's sitting between 2 carbons, okay? So it can't really be that polar, okay? So, basically, this structure now is very, very hydrophobic, because if we were to actually stick this oxygen facing out into the blood, we'd have a huge, great long-chain carboxylic acid group sticking off the side, which is extremely hydrophobic. So we can't now put these in the phospholipid monolayer of our LDL molecule. Instead, we are going to dump these cholesterol esters, which I'll just abbreviate to CE now. C for cholesterol, E for ester. We're going to dump them into the hydrophobic core of our LDL molecule, and that now completes our structure in LDL molecule. We have the phospholipid monolayer on the outside, made up of mainly phospholipids. And I should have said this actually when we're discussing the phospholipid monolayer. The main phospholipid that you have is lecithin. It's phosphatidylcholine. That's the main one that makes up LDL particles, phospholipid monolayer. Okay, and then we also have dotted around the place cholesterol molecules, which are free and therefore have that nice alcohol group that can phase out into the blood. And then we have this great big apolipoprotein B100, and then in the middle we have cholesterol esters stored within the hydrophobic core of the LDL molecule. Now, this is the structure of LDL, and the role of this is to deliver cholesterol to cells, okay? Now, it performs an important physiological role, but if the level of it is too high, then this promotes the formation of atherosclerotic plaques. Okay, so in the next video, what we'll then start off with is the pathogenesis of atherosclerosis.